the moon, a dead world, or a cosmic enigma. At first, this wasn't supposed to be a mystery. It was just a simple idea. Look at everything we know about the moon. All the missions, all the data, from Apollo to modern orbiters. Put it together, see the full picture. Because individually, each mission tells a story, but together, they should tell the truth. So I started going through it. Apollo missions, seismic data, surface samples, then later missions, orbiters mapping the surface, measuring composition, scanning for water. At first, everything seemed consistent. The moon was what we thought. A dead world, no atmosphere, no activity. Just a frozen record of the past. But then, small things started to stand out. Details that didn't quite fit. Data points that felt off. Nothing dramatic, nothing that immediately changes everything, but enough to make you pause. For example, why were there seismic readings at all? Why did the moon move? Then there were surface features that looked younger than expected. Cliffs that suggested the moon was still shrinking, still changing. And then the water. Ice. On a world that should have lost it billions of years ago. At that point, it stopped being a simple review, because the more data I looked at, the more the same pattern appeared. Different missions, different decades, same inconsistencies. And that's when it became something else. Not just information, but a question. What if we didn't misunderstand one thing about the moon? What if we misunderstood the entire picture? Because individually, each anomaly can be explained, but together, they start to form something bigger, something harder to ignore. And that's where the story begins. The Apollo missions were supposed to answer everything. Humans landed on the moon, walked across its surface, collected samples. For the first time, we had direct evidence. And at the time, it felt complete. The moon was dry, cold, inactive, a finished world. But when you look closer at the data Apollo left behind, the picture isn't that simple. Because Apollo didn't just bring back rocks. It left instruments, seismometers, reflectors, experiments designed to keep working long after the astronauts left. And those instruments kept sending data that raised questions. One of the biggest was seismic activity. The moon wasn't still, it was shaking. At first, that didn't seem like a problem. Impacts from meteoroids were expected. Thermal expansion could explain some movement, but that wasn't all. There were deep moonquakes, recurring, predictable. And then there were shallow ones, stronger than expected, long-lasting. That didn't fit the model of a completely dead world. Then there were the samples. Lunar rocks showed signs of a more complex history than we expected. Evidence of past heating, melting, differentiation. The moon had been active at some point. But the bigger question was it completely inactive now? Apollo didn't answer that clearly. It suggested answers, but it also left gaps. And at the time, those gaps weren't a priority, because the mission had already succeeded. We had landed, we had returned, the focus shifted elsewhere, but the data remained. And decades later, when you go back and look at it again, you start to notice something. The Apollo missions didn't just give us answers. They left behind questions we never fully resolved. When I went deeper into the Apollo data, one thing kept coming up: moonquakes. At first, they seem easy to explain. The moon gets hit by meteoroids, it heats up during the day, and cools at night. Of course, it would shake a little, but the more you look at the data, the less simple it becomes. Because there isn't just one type of moonquake. There are several, and some of them don't behave the way they should. The first type, impact quakes, are expected. Objects hit the surface, energy spreads, and the ground vibrates. No mystery there. The second type, thermal quakes, come from temperature changes. The moon experiences extreme swings between day and night. That expansion and contraction creates stress in the surface. Again, expected. But then you get to the deeper ones. Deep moonquakes. These happen hundreds of kilometers below the surface. They occur regularly, in repeating cycles, almost like a pattern. And they are linked to Earth, specifically to Earth's gravitational pull. As the moon orbits Earth, tidal forces stretch it slightly. That creates internal stress and releases energy, which means the moon is still responding dynamically, still moving internally. But the most difficult to explain are the shallow moonquakes. These occur much closer to the surface, and they are strong. Some reach magnitudes comparable to earthquakes on Earth. But what makes them strange isn't just their strength, it's how long they last. On Earth, seismic waves fade quickly. Water, atmosphere, and active geology absorb the energy. On the moon, there's nothing to absorb it, so the ground keeps vibrating for minutes, up to 10 minutes in some cases. The moon doesn't just shake, it resonates, like a bell that keeps ringing long after it's struck. And here's where the pattern starts to form. These quakes are not random. Many of them occur in similar regions, near features like lobate scarps, signs that the moon is still shrinking, still cooling, still changing. That suggests a connection, internal stress being released over time. But even with that explanation, what do you think? Comment, I need to see your perspective. It doesn't fully close the gap, because a completely dead world shouldn't behave like this. It shouldn't have this level of internal response, this level of structure. And when you compare this data to modern observations, the same question comes back. Is the moon really inactive, or is it just quieter than we expected? Because there's a difference, and the data points towards something in between. Not alive like Earth, but not finished either. And that matters, because if the moon is still releasing energy, still adjusting, then we don't fully understand its current state. And that means everything built on that assumption needs to be questioned. If there's one discovery that completely changed how we see the moon, it's water. Because for decades, the conclusion was clear. The moon was dry, no atmosphere, no protection from the sun. Any water should have disappeared billions of years ago. That idea was accepted until the data started saying something else. At first, it was subtle. Orbital missions detected traces of hydrogen near the poles. Weak signals. Easy to question. But they kept appearing. Different instruments, different missions. Same result. Then came stronger evidence. Impact experiments showed that when material was ejected from certain regions, it contained water molecules. Not a lot, but enough to confirm something important. The moon was not completely dry. And the pattern was clear. The water wasn't spread evenly, it was concentrated at the poles, specifically inside craters that never see sunlight. Because of the moon's low axial tilt, some regions remain in permanent shadow for billions of years. Temperatures there drop below -200 degrees Celsius, cold enough to trap water ice indefinitely. These areas became known as cold traps, places where molecules can survive without evaporating. And inside them, water accumulated, delivered by comets, created through interactions with solar wind. Over time, migrating across the surface until it reached a place where it could stay, locked in darkness. But here's what makes this more than just a discovery. It wasn't expected. We didn't go looking for large amounts of water. We assumed it wasn't there. Which raises a bigger question. What else did we assume? That isn't true. Because water changes the entire picture. It means the moon is not chemically static, not completely inactive. There are processes happening, slow, subtle, but real. Molecules forming, moving, settling, a kind of cycle. And that matters for more than science. It matters for exploration. Water is a resource. It can support human missions, provide oxygen, fuel. It turns the moon from a destination into a place we can stay. And that's exactly why modern missions, including Artemis, are targeting the lunar South Pole. Not randomly, but because that's where the evidence points, where something unexpected was found. And when you add this to everything else, moonquakes, surface changes, magnetic anomalies, a pattern starts to emerge. The moon isn't what we thought, and the more data we gather, the harder it becomes to ignore that. The moon doesn't have a magnetic field. That's one of the first things you learn. No global magnetosphere, no protective shield like Earth's. It's too small, its core is too inactive. So the assumption is simple: no magnetism. But when you look at the data, that's not entirely true, because parts of the moon are magnetized, not everywhere, but in specific regions. Localized patches of crust where magnetic fields exist, stronger than they should be. These are called magnetic anomalies. and they don't behave the way we expect. They are scattered, irregular, disconnected from each other, not part of a single system, almost like fragments of something that used to exist, but doesn't anymore. Some of these regions are strong enough to interact with the solar wind, deflecting charged particles, creating tiny, localized mini magnetospheres. That alone is unusual. But what makes it more interesting is what we see on the surface. In certain areas, the moon has strange, bright patterns, swirling shapes that don't match impact craters or geological formations. They're called lunar swirls. For a long time, no one knew what caused them. They don't follow terrain, they don't align with known processes. But when you map them, they line up with magnetic anomalies. Where the magnetic field is stronger, the surface is protected from solar wind. That slows down space weathering, the process that darkens the lunar surface over time. So those regions stay brighter while everything around them gets darker. What you're seeing is a visible map of invisible forces. But that still doesn't answer the main question. Where did these magnetic fields come from? One theory is that the moon once had a global magnetic field. Billions of years ago, a dynamo in its core, similar to Earth's, that eventually faded. The anomalies we see today would be remnants of that ancient system, frozen into the crust. Another theory suggests massive impacts created them. High-energy collisions could have temporarily generated magnetic fields, imprinting them into the rock as it cooled. But neither explanation is complete. Some anomalies are too strong, too structured, and their distribution isn't fully understood. Which brings us back to the pattern: seismic activity, water, surface movement, magnetism. Individually, each one can be explained, but together, they start to suggest something else: that the moon's history, and possibly its present, is more complex than we assumed, and that there are still parts of it we don't fully understand. The moon looks unchanged, a frozen landscape locked in time for billions of years. Craters everywhere, dust covering everything. At first glance, nothing moves. But when you compare data over time, that idea starts to fall apart, because the surface is not completely static. It changes, slowly, subtly, but consistently. One of the clearest signs is the presence of lobate scarps, long, cliff-like structures formed as the moon cools and contracts. As the interior loses heat, the entire body shrinks slightly. That forces the crust to adjust. It cracks, it folds, it rises, creating features that weren't there before. And these are not ancient. Some of these scarps are relatively young, which means the process is still happening. The moon is still shrinking, still evolving. Then there's seismic activity. Moonquakes don't just shake the interior, they affect the surface. In some regions, there is evidence of landslides, material shifting down slopes, triggered by vibrations. Even in low gravity, movement happens. Over time, small changes become visible. Then there's the dust. The moon's surface is covered in fine particles, regolith. With no atmosphere, you might expect it to sit still, but it doesn't. Sunlight can charge particles electrostatically, lifting them slightly off the ground. Allowing them to drift, move, settle elsewhere. It's not wind, but it is motion. Even astronauts during the Apollo missions reported seeing a faint glow near the horizon, possibly caused by this floating dust. A surface that looks still, but isn't. And when you connect this with everything else, seismic activity, surface contraction, electrostatic movement, a pattern becomes clear. The moon is not frozen in time. It is quiet, but active. And that means what we see today is not the final version. For a long time, the moon felt finished. Apollo had done its job. We had gone, studied it, and moved on. But modern missions changed that. Orbiters began mapping the moon in ways we couldn't before. Higher resolution, better instruments, more precise data. And with that, the narrative started to shift. The moon was no longer just a relic. It was a system we didn't fully understand. Missions like the Lunar Reconnaissance Orbiter revealed new details, surface features that looked younger than expected, evidence of water in permanently shadowed regions, temperature extremes we hadn't fully measured before. Each new dataset added something. But more importantly, it reinforced the same pattern. The moon wasn't as simple as we thought. And that brings us to now, because for the first time in decades, we're sending humans back. Not to repeat Apollo, but to go further. Artemis II is the next step, a mission that will send astronauts around the moon, not landing yet, but preparing for what comes next. And the goal is different. Apollo was about reaching the moon. Artemis is about understanding it, about staying, about building a long-term presence. And that changes everything. Because if the moon is more active than we thought, if it has resources, instability, unknown processes, we need to know. Before we land again, before we build, before we commit. Artemis II is not just a mission, it's a transition. From exploration to investigation, from short visits to long-term plans. And the reason we're going back is not just ambition, it's uncertainty. Because after decades of data, we've realized something important. We don't fully understand the moon. Individually, none of these discoveries are shocking. Moonquakes can be explained. Water ice can be explained. Magnetic anomalies, surface movement, each has a theory. On their own, they don't change everything. But when you put them together, something different appears. A pattern. Different missions, different decades, different instruments. Same conclusion. The moon is not completely inactive, not completely understood. It is something in between, a world that looks simple, but isn't. Because the same themes keep repeating. Internal activity, surface change, hidden resources, unexplained magnetic behavior. Each one points in the same direction, not toward a single discovery, but toward a shift in perspective. We didn't get one thing wrong. We simplified the entire system. We assumed the moon was finished, that its story was complete. But the data suggests otherwise. It suggests that the moon is still evolving, still reacting, still holding information we haven't fully interpreted. And that changes how we look at everything else. Because if something this close to Earth, something we've already visited, can still surprise us, then what else have we underestimated? This isn't just about the moon. It's about how we understand worlds. For a long time, we believed that small bodies cool down, become inactive, and stay that way. That once a planet or moon loses its heat, its story is over. But the moon challenges that idea, because it shows signs of activity, even after billions of years. Subtle, slow, but real. And that changes how we look at other places. Moons around Jupiter, moons around Saturn. Distant rocky worlds. If the moon isn't completely inactive, then maybe those worlds aren't either. Maybe activity doesn't require size. Or extreme heat. Maybe it just requires the right conditions. And that expands the possibilities. For geology, for chemistry, for life. The moon is close, accessible, and still not fully understood. Which means we're not just studying it, we're using it to rethink everything else. So okay, we went to the moon. We studied it, measured it, brought pieces of it back, and we thought we understood it. But looking at all the data together, that confidence doesn't hold. Because the moon isn't silent, it isn't frozen, it isn't finished. It moves, it changes, it hides things we didn't expect. We didn't miss one detail, we missed the pattern. And now we're going back, not to confirm what we know, but to find what we didn't see.